Hello, welcome to Empowering Healthcare through NLP, harnessing clinical document insights here at Intermountain. We're going to be introducing ourselves and highlighting a few projects that we have worked on so far with John Snow Labs, PIID identification, chart abstraction, and summarization. We're going to talk about some lessons learned and some future plans. I am Dylan Wagenseller. I have a computer engineering degree at Clemson. I've worked with healthcare data ever since. In the same year, I got bit by a bat and stung by a stingray.
Hi, everybody. My name is Yinxi Zhang. I'm a staff data scientist at Databricks. I have a PhD in electrical engineering from University of Houston and have been with Databricks for 3 years. My fun fact is I have adopted a garden bed at a community garden, and that's a picture of it. Handing over to you, Dylan.
Here's a little overview of what we have here at Intermountain Health. 374 billion rows, 13 million patient records. We have over 400 million individual patient notes, 33 hospitals, 385 clinics. We're currently in the process of migrating to Databricks. We just merged with SEL Health, who was a Epic customer. We are currently a Cerner customer, but going over to Epic. The plan is to get everything onboarded, raw data into the bronze layer tables, and then we're going to create a common data model into the silver tables and then present all that to our customers. And then the John Snow Labs and the pipelines and all the LLM work will be happening on the silver layer as well. These are the projects that we're going to be talking about. The de-identification uses name entity recognition. Chart abstraction, we're going to try to use a vector search. And for note summarizations, we not only use John Snow Labs, but a couple open source LLMs as well. The individual blobs, the notes themselves, have been a bit of a black box for a while. It's all unstructured data, so the only way to get any useful information from them has just been using fuzzy logic, regex. And the great part about LLMs is not only can we structure that data, but we can also de-identify it. And that way we can send that data to researchers and other third parties, and they don't have to go through the whole IRB, the approval process, and which can be a long, drawn-out process. So it helps be able to present this data that otherwise wasn't presentable. The starting point for us at John Snow Labs was first we needed to get a trial license. We worked with Karen Thompson at John Snow Labs, and she's been great. You can also apply for one on their website. When looking up if de-identification or how to de-identify data at Databricks, the first note that Databricks presents to you is a notebook that contains another customer that used John Snow Labs as well. So that was a great reference material for us in doing this project. We also had direct assistance from John Snow Labs as well during our trial period, which was paramount. The great part about John Snow Labs and this LLM process is you don't have to be a data scientist or have a data scientist background. I only know Python and PySpark, and I was able to utilize this and get a full production level ready pipeline from beginning to end. Creating the pipeline is pretty straightforward. It's just setting up functions to take the unstructured data and convert it into sentences and then chunks, and then name entity recognition to then take those chunks and remove any PHI out of it. So you just start with a raw unstructured data in a PySpark data frame, feed it through the pipeline, use explode and zip to take that output and put it back into the format that you ultimately want and place it back onto the database. The thing that took us the longest was figuring out how to scale on the millions of documents that we have. The data that we were sending to the pipeline wasn't partitioned. So the first big fix or catch was let's partition that data before actually sending it through the pipeline. So with 1,000 notes, 1,000 partitions, it took about 2 minutes. When scaling it, however, was interesting in that when we try to do 10,000 notes, 10,000 partitions, or 10,000 notes, 1,000 partitions, Databricks wasn't able to finish it. We were only using CPU cluster, and it was a 8-worker, 448 gigabytes of memory with 128 cores, and a driver of 32 gigs of memory. So we had a pretty sizable box. So it don't know if the cluster itself was a limitation, but in order to scale it to our millions of documents, the best way we found was just taking 1,000 notes, 1,000 partitions, and just looping with that. Even when trying to double it, it more than tripled the total time. So that's why we stuck with what we found was the most efficient. The next thing that's extremely important is in order to get the best output, we combined both the two de-identification models from John Snow Labs, but to get better accuracy. But as a caveat, this data here has been manipulated. It's not our real employee names and stuff. But one of the couple PHI misses it had was phone numbers and emails, and we brought that to John Snow Labs, and they already have regex to fix that, which is great. The other one was we were missing a few dates. And so as you can see in some of these examples, the date itself was tied with the word on. And so it didn't know that it thought that as a single chunk. And so it didn't strip it out. So we would need to come up with a manual process or a regex to catch those as well. Any data, any PHI leak can be hundreds of thousands of dollars. So if you ever utilize this models, you have to validate and check and do an iterative approach in making sure that you can remove as much PHI as humanly possible. Faisal and Jerry did a great talk on this last year on the accuracy and the metrics that they were finding with their models. So I'd recommend to check those out. Another project that my teammates, Brandon, worked on was chart abstraction. This is a model of how we perceive that we're going to provide that data to our customers. Our stroke chart abstractors have to read through tons of notes and find individual pieces of information in order to answer hundreds of questions. So there's about 900 questions total, and some of them are discrete and some require the notes themselves. So we want to provide what questions that we can answer for them, metadata about the note itself, what we think the answer is, how we found that answer, the context of the note itself, and how confident we are in that answer. We also want this to be a feedback loop as well, because we need their input to let us know how accurate are we doing, just in case we need to manipulate the regex and what we're doing with it. Finally, this is how the process works. So similar to the de-identification, you start with an unstructured note. You then apply the John Snow Lab models to get metadata and structured information about that note. And then we strip out any data from that note that isn't otherwise needed. And so then we're just left with structured note data that we know can answer questions, and then using regex and other matching algorithms, we would then give the answers to the questions that we think they can answer. And then it would be a feedback loop of we would either manipulate what we're trying to use to grab the answers that we need for their questions, or we go and look for more note data.
All right. Thank you, Dylan, for introducing the de-identification and chart abstraction use cases. The other use case we work together on this is a summarization pipeline. It is designed to be integrated with the electronic healthcare system in the end to generate automated transcription for detailed patient notes. Providing concise and accurate summary from patient notes can help reduce the information overload for healthcare providers and facilitate effective communication. This way, they can focus on quality patient care rather than spending excessive time on paperwork. The main challenges in implementing the summarization pipeline are, first of all, deal with extremely long context, and then second, how to scale this for large scale data. We'll talk about how to deal with long context first. You can see from the histogram of the token size from the patient note, it has a long tail of patient notes that have more than 4,000 token size. This makes it impossible to fit into any summarization model or any generative LLM model like Llama or Mistral in a single run. The first thing we do is to pre-process the raw text as much as possible. We segment the nodes, trying to extract key sections based on some empirical regex rules so that we can get sections, for example, we can get sections for some information like vital measurements, history of present illness, or current assessment and plans. And with after the segmentation, some of the nodes will still have longer context. Then we apply chunking strategies so that it can capture as much relevant context as possible in a given chunk. And with the chunked and pre-processed doc, we summarize each section separately. This is where, Dylan, could you flip to the next slide, please? Mm-hmm. This is where we utilize the map reduced chain module in LangChain. So it has two main components. Map is to apply the summarization pipeline to each chunked document individually. And then it has a reduce module where it combined all the mapped output to provide as an input to the summarization pipeline and generate the final response. Next slide, please. In terms of model choices, in this implementation, we use an open source model from Falcons AI. This is a medical summarization model. It's a fine-tuned T5 model on medical context. We'll talk about alternatives in the slides later, but here let's focus on this implementation, the reason and benefits why we choose the sequence-to-sequence T5 variant model. First of all, you don't need to design prompt for it. And then secondly, with the smaller model size, it makes it much flexible and easier to generate batch inference offline. Then sequence-to-sequence model has generally has less hallucination compared to generative models like GPT or Mistral. In terms of deal with the long context, the sequence-to-sequence model have shorter input token size. The maximum input token size is 512, which is relatively less comparing to generative models. So we use the MapReduce chain to compensate that. When it comes to inference, we actually package the entire chain using MLflow LangChain flavor. This provides a good standardized way for online and offline inference. We only implemented offline inference due to security and infra reasons, but packing the chain as MLflow model flavor makes it flexible for future online inference extensions. Next slide, please. And this is how we do the batch inference. We basically wrap the model as Spark Pandas UDF, so it can be scaled to multi-node GPU clusters. This way, we can scale out the computation and increase the efficiency by adding more worker nodes to the GPU cluster. In terms of performance tuning, we mainly tuned the summarization pipeline batch size and the task parallelization in Spark GPU cluster configurations to maximize the GPU utilization. The other trick we did for the batch inference is to process the entire table as micro batch streams. This has a little bit more overhead comparing to like a full batch solution in a single run. But the good benefit we get from this is to have a better error recovery strategy. This way, if some edge cases we haven't caught errored out in the process in one of the patient nodes, we'll still be able to recover from a checkpoint from the Spark structure streaming to restart the process after fix the issue. So we don't need to reprocess from the beginning and from scratch. Next slide, please. All right, here we want to summarize a little bit of lesson learned from all those use cases. First of all, real life data is very messy. We try to whenever developing NLP applications or LLM use cases, we try to understand as much insights as the data possible so that we can design the best data preprocessing and chunking strategies for better quality of LLM application. It's all like trials and errors. So from what we learned, it's really important to build the code as modular as possible to handle future enhancement or to provide flexible interface for different parameter tuning, and also create a structured evaluation process so that we can always trace back to the impact of different parameters. The second point we want to highlight here is scalability. We mentioned the challenge about scaling to millions of nodes multiple times throughout the conversation and presentation here. Some of the key tools we have utilized to scale the inference is to use Johnson Labs pipelines, which is backed by Spark in the backend, and also for open source and lane chain modules, we use Spark Pandas UDF to do the scaling. Last but not least is how to enhance and improve the applications. We thought about alternative approach using generative LLMs, and those are here with this like two potential alternative options for the summarization use case and for the chart abstraction. When it comes to summarization, we're now using a smaller sequence-to-sequence model, but we can use generative models with prompt engineering, where it has longer token context that will help capture help capture relevant context better. And to reduce the hallucination, we need to build some guardrails if we choose to do prompt engineering. And then for the chart abstraction, now it's mainly document retrieval, and we can add a generative component to it so that it can generate the survey output result automatically and reduce some of the human involvement in the process. Now I'll hand over back to Dylan to, oh, sorry, there's one more slide about where we're heading to. So now, throughout the conversation, the three main use cases, we have implemented and vetted approaches using named entity recognition and sequence-to-sequence models. Where we're heading to is to explore the benefits of generative models further using prompt engineering, RAG, and also when we get more mature, we can do like fine-tuning existing foundation models or even pre-train our own foundation model from scratch. All right, now I'll hand over back to Dylan to talk about the future NLP roadmaps at Intermountain House.
Thanks, Yinxi. Yeah, we're doing a lot of great stuff here at Intermountain. Like I talked about before, the de-identification, we're on the cusp of once we get that finalized, a couple things iterated around making sure we catch those phone numbers and emails, we're good to go. And the note summarization and the chart abstraction, we're in the midst of it. We are developing at this moment, and it's looking good and promising. And we also have a couple future projects that we've already started to look at with HCCs is going to be a big one, and it's going to be exciting to work on. We also have a surgical cohort opportunity. So some data only exists in the notes themselves. For example, on knee arthroplasty, there is no discrete data to show if it's unilateral or bilateral. So we want to utilize Johnson Labs and name entity recognition to catch those keywords so that we can better group these patients into their individual cohorts. And finally, clinical documentation improvement. We want to be able to help more accurately document CPTs and diagnoses and everything else when it comes to needing to document something. LLMs can assist all of our caregivers. And finally, we want to give a couple acknowledgments, some shout outs. Brandon Jenkins here at Intermountain Health is doing amazing work with the chart abstraction. Andy Merrill and Michael Biene, great to work with. The Ernest and Young team, the EY team, Saravan and Vilu, they are doing all of the research around making sure that the notes that we eventually will be able to send out are truly de-identified. Gursev and Karen at Johnson Labs have been instrumental instrumental in our work. That they're amazing, and it's great to have a resource like Gursev, and that we could have spent weeks trying to figure out how to make those pipelines more efficient, and he knew exactly what to do, and it worked great. And finally, Charles and Stephen at Databricks. This isn't everybody, but we just wanted to give a couple shout outs to everyone and really appreciate it. And thanks for your time.